Okay, in this video we're going to go ahead and build some polynomials from known attributes. So that means is that in the last video series we went ahead and we had a polynomial and then we got to break down its attributes from it. Now this we're going to go ahead and not get the polynomial per se from the beginning, but we're going to go ahead and we're going to get some zeros and some attributes of it, and then we're going to be furnishing the polynomial itself. So let's get started. Okay, so here's what we're going to be doing in this video is how are we going to build polynomials from zeros. We're going to take a look at what is a conjugate. What are the properties of a conjugate and how do I use them to build polynomials? And what is the irrational conjugate rule and the complex conjugate rule, and how do we use them? Okay, so the first thing that we're going to go ahead and do is that we're going to take a look at examples of conjugates, okay? And basically what we're looking at is some patterns. So let's take a look at all three simultaneously. In this first one right here, notice that we have our x's, right? And we have our 5s that are the same, but we have a minus and a plus right here. And the same if I were to go ahead and we have the x's here, right? We're looking at the second one, and I have a square root of 5 and a square root of 5, and here's a minus and a plus right here. And then finally, for this guy, I have x's, right? And I have this business of a 5i and a 5i, and I have a minus and a plus right here. So what we're looking at if we have conjugates are usually are going to go ahead and be in this form of a minus b times a plus b. And the minus sign and the plus sign can be switched around as long as they are opposite one another. Okay, so that said, is that with the conjugates, let's go ahead and multiply some of these out and see what happens. Notice that this is going to go ahead and we're going to need FOIL. Okay, so let's go ahead and FOIL this guy out. X times x is x squared. X times 5 is 5x. Negative 5 times x is a negative 5x. And a negative 5 times 5 is a negative 25. So notice that in the middle, those go ahead and cancel out. And at the end of the day, we end up with x squared minus 25. Moving on to the next one. Doing some FOIL again. X times x squared. X times the square root of 5 is, x square root of 5. Negative square root of 5 times x is going to be a negative x square root of 5. And a negative square root of 5 times positive square root of 5 is going to just give us a negative 5. So remember is that any time that we have, for example, in two square roots that are the exact same thing, it's just going to equal the radicand there, okay? And the reason being is that if I have the square root of x and the square root of x, I can multiply these two x's up, and that would give me x squared, and the square root of anything squared is just going to be this. Okay, what is under the radicand? So, going back to our examples here, these are going to go out, and I end up with x squared minus 5. And then finally, these guys right here, one thing that we're going to have to remember that from past lessons that I squared is going to be a negative 1, okay? And so, that in mind, x times x is x squared. X times 5i is going to go ahead and give us 5ix. Negative 5i times x is going to give me a negative 5ix, and then negative 5i times a positive 5i, so I multiply the 5's together, that's going to give me a negative 25, because it's a negative times a positive, and then I squared. So what we have to do is that we have to drop in the -1 for the I squared. And let's also clean up that center, which we know that those are going to cancel out. And that's going to give me x squared. These guys canceled out. -25 times I squared, which is now a -1. So I get x squared plus 25. Okay, so take a moment and see what has happened in every single one of these examples here and why conjugates are useful. Okay, so what pattern did we notice? And one of the main ones, and there's several patterns, but an example answer would be that the centers, okay, and when I say the centers, when we do these all out in FOIL, the middle, I should say the middle terms cancel out. So we're going to use that to go ahead and write some polynomials with and discover some of these properties and whatnot that are going to help us build polynomials in a rewarding way. Okay, so we're going to go ahead and also need to review some of the rules that have to do with some of these square roots here, okay? So the first thing that I want to review is that anytime that we have square roots that you're multiplying with different radicands as a and b, you can move them under one radical sign that is going to just be a times b. So that said is that if I have the square root of 2 times the square root of 5, that's going to give me the square root of 2 times 5, which is 10. Okay? And likewise, if I were to move to this second example here, if I have the square root of 2 times the square root of 10, that's going to give me the square root of 20. Now, one of the things that we got to check for in both of these is that can I break them down? A 10 only breaks down into the 5 and the 2 that we had, okay? So that means is that I can't pull out any of the doubles, and so I just leave it simplified as is. However, with a 20, I get a 4 times 5 and a 2 times a 2. The 2's are paired up and come outside the radical sign, and I get 2 with whatever's left, the square root of 5. And like I had said in the last video, any square root multiplied by itself is just going to give us that number, okay? So looking at this business of square roots and fractions, if we have the square root of an entire fraction, we can take the square root of the numerator and the denominator separately. So for example, if I had the square root of 4 over 9, the square root of 4 is just going to give me 2, and the square root of 9 is 3. Moving straight across is that in this guy right here, I can rewrite this as a square root, well, I got the square root of 5 over 9. The square root of 5 is just the square root of 5, so I just leave it because I know that it's prime. I can't take the square root of it. However, I can take the square root of 9, which is going to give me 3. And likewise, so this basically means is that, let's look at the examples. Both the top and the bottom were perfect squares, so it ends up being a nice, clean fraction. Okay, the denominator only is a perfect square, so it goes down to 3. And the numerator is not a perfect square, so it has to stay. Is this the square root of 5? And now we're going to go ahead and take the square root of the top and bottom of this one, where the bottom is going to stay as a square root, and then we're going to have to clean it up. So the square root of 5 on the bottom is this going to be the square root of 5, and the square root of 4 up top is the square root of 2. However, if we have a square root on the bottom, mathematical, I guess, notation and is going to require us to move it to the top. And what we do is that we multiply the top and the bottom by itself, which is basically the square root of 5, which is going to give us square root of 5 times square root of 5 is 5, and then 2 times square root of 5 up top. So that moves the radical, which originally was on the bottom, moves it to the top, and then it fits for the standard for mathematical notation. Now, one of the things that we're looking at is that all of these guys were a solid yes, you can do that. However, we need to go ahead and also look at no's, okay? Now, students oftentimes, when we're adding these, okay, or subtracting these radicals, they want to go ahead and combine them up. And notice that you cannot do that. And one of the ways that I show students is, say if I were to go ahead and apply the rule that is not accurate from above, okay? So say if I were to say this is equal to this, okay? Can I prove that they are equal or not equal? And the answer is yes. Let's go ahead and break this down. So 9 plus 16 under the radical sign is going to give me 25. The square root of 25 is 5. However, if I were to do each one of these separate, the square root of 9 and the square root of 16, I would get 3. Square root of 9 is 3. Square root of 16 is 4. And that would give me 7. So that shows us that they're not equal. And so this is definitely not a property. So we need to go ahead and keep that in mind when we're asked to break some of these down in the next parts. Okay, so let's go ahead and build some polynomials here. So first things first is that we're going to read the prompt, and it says find a possible, I like that word, okay, we're going to come back to it and see why it's important, with all integer coefficients. And remember, integers are going to go ahead and be all the numbers on a number line, okay, that are going to be 0 through 1, 2, 3, 4, 5, all the way to infinity, and the opposite, so all the negative numbers of those. And zeros of these guys, okay? So the zeros, we have x equals a negative 3, x equals 2, and x equals 0. So notice that it's opposite from the lessons that we've had previously because the zeros are given to us. And from here, we're going to go ahead and find a possible fully factored form and then use that to go ahead and multiply out the polynomial and then take a look at its attributes. So let's go ahead and see what to do first. Okay, so we have the zeros, and we know that the zeros are answers to factors of a polynomial that are set equal to 0. So what we're going to do is that we're going to work backwards to find this fully factored form. I'm going to take each one of the zeros and try and get this so each one of these are going to equal 0. Now, how am I going to do that? So for this guy right here, I'm going to add 3 to both sides, and that's going to give me x plus 3 equals 0. And I'm going to subtract 2 from each side, and I'm going to get x minus 2 equals 0. And this guy just already equals 0. So that means is that these right here are going to be factors of the polynomial or possible polynomial that we're looking for, because that gives us, when they're set equal to 0, these answers. So in the fully factored form, I'm going to write f of x equals x times x minus 2 times x plus 3. Okay? So let's go ahead and fill out the rest. Since we know the zeros, that means is that we know the x-intercepts. So bringing these down, just like we did in the last lesson. Okay. The y-intercept of the polynomial. So we go ahead and we can, and this is something that we're going to do in a few, but let's go ahead and plug in for just ease of calculation right now. Plug in 0 for x to get the y-intercept. Okay. So this means that this is multiplying by 0. So that's 0, a negative 2, and a 3. So we know that it's a 0. So 0, 0. Okay. So pretty good so far, filling everything out. So what I want to do is I want to find the polynomial in its standard form as well, okay? Because we got the fully factored form. So let's go ahead and multiply out this polynomial so we can get it in its standard form, and then I just kind of want to write it right here, okay? So let's multiply this out. We have x times x minus 2 times x plus 3. So I'm going to multiply these using FOIL first and just bring the x down. So we'd get x times, and then I multiply x times x, which is x squared, x times 3, which is 3x. Negative 2 times x is a negative 2x, and a negative 2 times 3 is a negative 6. Clean up the center here, and that's going to give me a negative 1. So I'd have x times x squared. I'm sorry, that's going to give me a positive 1, plus x minus 6. And then, using the distributive property, I'm going to go into each one of these, and that's going to give me x to the third plus x to the second minus 6x. So, when I multiply this all out in standard form, it's going to be x to the third plus x to the second minus 6x. So, that said, we can use that to do the end behavior. So the end behavior, I have a positive leading coefficient. So that's a is going to be 1. And I have an odd leading exponent. Okay, and I probably should put a as positive rather than 1. And so I know that positive and odd is going to have a polynomial end behavior of this. So as x gets really large in a positive direction, y gets really positive and large. And likewise, when x gets really negative, and then y is going to be getting really negative. So that said, that's the end behavior. And let's set up the x-intercepts. Okay, so it looks like we are ready to do some graphing, just like we did in the last video or the last lesson. So it looks like our polynomial is going to be something that looks like this. Now again, this is a possible polynomial, and when we flip the page here, I'm going to go ahead and show you why that is. Okay, so it looks like we did a pretty good job here doing a sketch, and notice that it has all the x-intercepts and all the zeros that it says that it's supposed to have. But one thing that I want to make sure that you guys know is that this is just a possible, okay, representation of that function, because remember is that the only thing that it needed to do is go through these zeros right here. Okay, and so if I call this f of x, there are an infinite amount of graphs that we could have went ahead and done out. We just kept it really simple. So for example, let me show you some of the possibilities. Okay, so highlighted through the blue one right here is the one that we graphed out. Okay, now if I were to go ahead and multiply my particular function, f of x, the whole thing by 2, notice that it would, and I'll highlight this in a different pattern, and that's what I did to generate these graphs. It's going to get the same basic curve, except it's going a little bit higher and lower in some parts. Notice that these remain the same, okay? So our zeros are going to remain the same. And if I were to multiply it by this business of 3, right, going like this, it's going to make things go higher and lower. And notice that it also is going to have the same x-intercepts, or zeros. And then finally, if I had to multiply it by a half, it would, or 0.5, it wouldn't have integer coefficients anymore. But it would go ahead and, again, we can see that there's going to be an infinite amount of graphs that are going to fit through those particular x-intercepts, okay, those zeros. So when it says possible, that's what it means. We're just trying to find one that happens to be in its simplest form where we don't multiply anything extra into it to change the shape. All right, so let's take a look at another one. Now this one right here, a lot of this verbiage from the last problem, but one of the things that we got to take a look at is the following, okay? Is that it is, again, a possible polynomial, all integer coefficients, and we have zeros of 3 multiplicity 2 and 0 multiplicity 3, okay? So let's go ahead and just write these out in our, down below what the zeros are, because it gives it to us. So we got 0, or I'm sorry, x equals 3 multiplicity 2, and x equals 0 multiplicity 3. So what I'm going to do is that I'm going to set this up kind of, forgot to write the 3 there, so we can go ahead and see how we're going to build this polynomial from each piece broken down here. Okay, so for the zeros there, notice that we have x equals 3, the multiplicity 2, so there's 2 of them, and x equals 0, okay, multiplicity 3, there's 3 of them. And so what we're going to do is that, just like we did in the last video, is that get them set equal to 0. So that means is that I'm going to subtract 3 from each side. I get x minus 3 equals 0. And this one is going to work out the exact same way. And I get x minus 3 equals 0. And the zeros over here, these are already set equal to 0. So this, right, all of these guys are going to be our fully factored form. And since we have multiple of them, I have x minus 3 to the second power, right, multiplying these out. And when I multiply all 3 of these out, I get x to the third. So the fully factored form is going to be f of x equals x to the third times x minus 3 to the second, okay? So let's start bringing down the other information that we have. The x-intercepts, remember we don't need to write the multiplicity, so the x-intercepts are going to be 3, 0, and 0, 0, okay? Plugging in f of 0 into the fully factored form to go ahead and get the y-intercept. We're going to go f of 0 equals 0 cubed, 0 minus 3 squared. We know that this is going to be 0 times, let's see, negative 3 squared times 9, which is just going to give me 0. So the y-intercept is 0, 0. Okay. So what we want to do is that we want to multiply them out. Okay. So we can have our final form here and see what that looks like. So we're going to get x to the third, multiplying this out. And I get x minus 3 times x minus 3. Let's FOIL this. X minus 3 times x minus 3 is x squared. Negative 3x. Negative 3x. And plus 9. That all multiplied by x cubed. Gather up like terms. I got x cubed times x squared minus 6x plus 9. And then I multiply the cubed into each one of those, and I get x to the fifth minus 6x to the fourth plus 9x to the third. And so my function in standard form, or my possible polynomial function in standard form, is x to the 5th minus 6x to the 4th plus 9x to the 3rd. Okay? From that, I can go ahead and find the end behavior. So I have a is going to be positive, and n is going to be odd. And so I have a positive and odd, which is going to look like this. And so I go ahead and say, as x gets really big in the positive direction, y gets really big in the positive direction. And as x gets really big in the negative direction, y gets really negative in that direction. Okay, so that said, let's go ahead and graph it out using the intercepts and the end behavior. Okay, so something to keep in mind is our lesson from, our previous lesson here, is that there is going to be an odd multiplicity here and an even multiplicity here. So remember, odd multiplicities do that little squiggly through the point, and evens bounce off of the x-axis, okay? They're tangent to it. So let's go ahead and see if we can make one of these guys, okay? So I'm going to say that it's going to come up and do one of these, and then come back down and do one of those. So that way, again, we have the multiplicity that odd does that little squiggly through there, okay? And then we have this even one where it is going to bounce off the x-axis. So let's see how we did. Okay, it looks like we did a pretty good job here. Notice that the intercepts are going to go ahead and be the same, and also we got this business of the multiplicities in full effect there along with the end behavior. So pretty good. Okay, so before we start this one off right here, we do need to change something that I caught at the last minute here. And so this negative square root of b has to be down here. And then what got cut off is as well. All right, so now we're ready to go after we fix that. So basically, what we're looking at is the same type of problem. We got this possible polynomial, integer coefficients, and the zeros of, okay, the square root of 7 and 1. Now what's different is that we have a 0 that is going to be in a rational number, and we want integer coefficients, okay? So that basically means, how is this going to work out? And this rule is the one that that had a part left out, is going to help us out. The irrational conjugate rule, okay? So it says if b is a 0 of a polynomial with all integer coefficients, then negative b is as well, okay? So that basically means is that the following. So I'm going to have the zeros, as stated above, are going to be 1 and this guy. Now, what they're saying is that if I have the square root of b, which is the square root of 7, then that means is that by the rule, I need one of these as well. And again, the rule is going to work for, say, if I had a negative right here, then this would just be a positive, and vice versa, okay? So let's go ahead and take a look at this thing in its fully factored form, if you will. Okay, so we are after this fully factored form, and what we're going to go ahead and do is that we're going to do the same thing that we have been doing in the first couple examples, and we're going to get these set equal to 0, subtract 1 from each side, and that's going to give me x minus 1 equals 0. I'm going to subtract, the square root of 7 from each side. Let's go out, and that is going to give me x minus the square root of 7 equals 0. And likewise add the square root of 7. Oops. I'm goofed up here. Square root of 7 each side. So I got x plus the square root of 7 equals 0. Okay, and so the fully factored form is going to be f of x equals x minus 1, x minus the square root of 7 times x plus the square root of 7. Okay, now if we want to find the x-intercepts, we're just going to be bringing down the 0. So we would have 1 comma 0, square root of 7 comma 0, and the negative square root of 7 comma 0. Okay, the x-intercept, or I'm sorry, the y-intercept, plugging 0 into the fully factored form, which is going to go f of 0 equals 0 minus 1 times 0 minus the square root of 7 times 0 plus the square root of 7. Okay, so this is a negative 1 times a negative square root of 7 times positive square root of 7. So when I multiply the square root of 7 times the square root of 7, that's going to give me 7. And the two negatives, so this is going to give me 7. So 0, 7 is going to go ahead and be my y-intercept. Now, this is where I know that we're going to be building the polynomial in standard form. So when I multiply this out, and I'm going to clear out some room here. Okay. So when we start multiplying out all of these factors from the fully factored form, notice that from this part right here, we have the conjugates that we practiced at the beginning of the lesson. So that means is that let's go ahead and tackle those first. So I got x times x, which is going to be x squared. And again, just doing the FOIL out. Oops. That guy, and square root of 7, and then the negative square root of 7 times square root of 7, so it's going to give me negative 7. Now, notice what happens. These cancel out, and we are left with x squared minus 7, and we have x minus 1 being brought down. Notice that putting all the pieces together is that we want integer, oops, wrong button, integer coefficients for our polynomial. Notice that by multiplying by the conjugate that all the square roots go away, and I'm left with just some nice integer numbers. And now I can just multiply this out to get my standard form of my polynomial and complete the problem. So x times x squared is going to give me x cubed. X times a negative 7 is a negative 7x. And just bringing everything down, foiling like we know how to. And here we go. So putting this in standard form, remember we got to have it from highest exponent down to the lowest exponent. So therefore, let's go equals x to the third minus x to the second minus 7x plus 7. Okay, so there it is in its standard form. And let's get the end behavior nailed down. I have A is positive, N is odd. So positive and odd, we're going to have something that looks like this. Okay. So again, as x gets really positively big, y gets positively big. When x gets really negative, y gets really negative. Okay. And so let's start to go ahead and put all the pieces on our graph so we can sketch it out. Okay, so there's everything kind of put out nicely here. Oops, I got the negative square root of 7 in the wrong spot. 1 second. Okay, so I have everything on the graph ready to go. We got the M behavior, we got our X and Y intercepts, and just a quality of life thing that the square root of 7 is approximately 2.6. So again, that's why I put them where they are. And it looks like we have no multiplicity, so we're just going to try and sketch this guy all the way through. And it looks like this would be a reasonable sketch for that guy. Okay, so let's see how we did with the computer-generated part. Okay, some more nice work by us. Notice again, x-intercept zeros, all the same, and behavior, and so everything looks pretty good. Okay. Now this guy right here, again, the same thing, except now we have a 0 that looks like this, okay, and a 0 that happens to be a 0. So, same thing as before, except we have this irrational conjugate rule that is going to go ahead and have a little bit of an addendum to it. So let's start off with our zeros just getting marked down like so. Okay, square root of 15. And let's see what the irrational conjugate rule states. It says is that if a plus b is a 0 of a polynomial with all integer coefficients, then a minus the square root of b is also, and vice versa. So that means is that if I have a positive sign in between them or addition sign in between them, then the conjugate's going to have a negative sign in between them. Well, we have a negative sign starting off with, so we know that there exists another, okay, irrational root that is going to exist as well. So we would have x, and then just changing the minus sign to a plus, 2 plus the square root of 15. Okay, and now we have all the zeros. So from here, let's go ahead and find out what this fully factored form is going to look like. Okay, so this one's going to play out a tiny bit different. And notice that I put some parentheses around these guys right here, these zeros. Okay, and the reason being is that it's a quality of life thing that we're going to just subtract from each side the entire thing, okay, and subtract from this side right here. I know it's written kind of funky, oops, and boy, I got myself smashed in here. Okay, so those go out, and so we would have, now watch the way that I'm going to write this, x, then minus, and then in parentheses, 2 minus the square root of 15. Okay, equals 0 from this side going out. Okay, and I'm going to be doing the same thing on this side over here, subtracting, or I should say on this 0 over here, subtracting that amount from both sides. Okay, those are going to cancel out, and I'm going to get, and I'm going to write it the same way, x minus 2 plus the square root of 15 in there equals 0. Okay, so if we're writing this in fully factored form, this is what it's going to look like. We would have this guy, and this guy. So let's write that out. Okay, and so what we're going to do is that we're going to go a little bit out of order in here, because what I want to show you is how to multiply out the fully factored form to get it in standard form. It's a little bit tricky, okay? So let's start with all of the factors lined up, ready to be multiplied. Okay, and what we want to do is that we want to attack these guys first, multiplying them out. So it's going to be a little bit of a tough, it's almost like a foil inside a foil, okay? So let's see if we can get this thing all worked out nicely, okay? So here we go. I'm going to FOIL and I'll try and do each part in different color. X times x is going to give me x squared. Okay? And then I will have x times this entire amount right here. So I'm going to go a negative x, because there's a negative sign in front, 2 plus the square root, of 15. The next part, okay? Now I have this times this, okay? Which is going to give me a negative x 2 minus the square root of 15. And then finally, I get all the way at the end this times this, okay? Which is going to give me, so there's a negative right here and a negative, so that's going to give me a positive, and then these two multiplied out. And we're going to have to do that separately in a moment, okay? So what we want to do is that we want to do some distribution, all right? And so when we distribute, we're going to get x squared, and mind you that this x is still chilling here, okay? So it needs to be added in later, just not right this moment. So I'd have a negative 2x minus x square root of 15 minus 2x plus x square root of 15. And then we need to multiply this out, okay? I'm going to show you how to multiply that out on a separate page right now, so one moment. Okay, just to give us some more room. So this very last part, we just need to multiply out using some FOIL. So we're going to get 2 times 2, which is 4. 2 times the square root of 15 is going to be 2 times square root of 15. Negative square root of 15 times 2 is a negative 2 square root of 15. And the negative square root of 15 times positive square root of 15 is a negative 15. These go out, right? And we end up with 4 minus 15, which is going to give me a negative 11. So we know that this part at the very end is going to be a negative 11. So I'm going to change this positive sign over here, and that's going to give me negative 11. So now I can cross out this and this and gather up everything, and then I still have to multiply in this x. So, but let's gather up everything first. So bringing down the x, and I get, x times x squared, gathering up these, a negative 4x minus 11, and then finally multiplying this back in to get our fully factored form of, let's get this, f of x equals x cubed minus 4x squared minus 11x. Okay, so that said, we can go ahead and from here just basically start knocking the other things out. But I know that was, you might not have seen that type of foiling before, so I wanted to get it out of the way first. Okay, let's get the x-intercepts and the y-intercepts and the m behavior all ready, and so we can check things out. Okay, so there's the x-intercepts. Okay. And then the y-intercept, I'm just going to plug it into our standard form. And so we would have f of 0, 0 cubed, and I think some of you already know where this is going here, but I just like to show all the process. 11 times 0, so we're just going to get a 0 out, so that's 0, 0. Okay. End behavior, we're looking at this guy right here. And so we know our n behavior is, we got a is positive and n is odd. So positive and odd, we know that we're going to go ahead and have this type of action. And so let's set up our graph and see what it looks like. Okay, so setting all those up, and I punched into the calculator these guys right here so we could get a decimal approximation. And so it looks like we have no multiplicities, and so this is a possible graph of a polynomial with all integer coefficients that have these zeros right here. So let's look at the technology and see how we did. All right, we have ourselves something that's all set up nicely. Notice we got our 7 and 7 right here, 1 and 1, and then these are the decimal approximations for our square roots of 7. So everything looks good. All right. Last example is going to contain a imaginary root, okay, or a complex root. And so this right here, we know that it is going to have a 0 of this and -4. So let's go ahead and take a look at this business of how we're going to put these pieces together. All right. So first things first, let's write down the zeros. X equals a -4 and x equals a -3i. And so let's take a look at how to deal with this 3i, because we haven't seen that before, at least in the setting of polynomials. So the complex conjugate rule says if bi is a 0 of a polynomial with all integer coefficients, then -bi is also. So that basically means is that we have to do the same thing, is that if this guy exists, then the opposite version of it exists as well, okay? So what we want to do is let's go ahead and get this thing written in its fully factored form. So we would just have f of x equals, and so let's go through all the steps. Okay, so there's all the zeros that are going to exist, and then I'm going to move everything on over to the left-hand side. Okay, so there are all of the factors, and so let's get those written down. Okay, and so we have this all written down, and so let's start to go ahead and take a look at this x-intercept, and this is where we got to go ahead and kind of hit the brakes. Is that this right here, when I bring these down, and to write 3i comma 0 doesn't make sense, okay, for an x-intercept, because we're only graphing on the plane that has real numbers, and we know that I is an imaginary number. And so these guys right here cannot be brought down into the x-intercepts, and the only real one that we have is a -4 comma 0, and these guys are not going to exist on that particular number plane, okay? So that's how one of the steps that when we have imaginary numbers, we got to go ahead and look at doing something different with that. So those don't exist, so our only real x-intercept is a -4 comma 0. But we can multiply these out to get a polynomial that is in standard form. So let's do that. Okay, and you notice that we got conjugate pairs again, like in the first part of the lesson, way back with the prerequisite skills. So let's go ahead and multiply out the conjugates first. So I'm going to get x times x, x squared. Okay. And doing this out, and I get a -9 and then I squared. Remember, I squared, as we reviewed, is a -1. Canceling out in the middle, okay? And we're going to be left with this business of x squared. Those canceled out, so I got a -9 times a -1, which is going to give me a +9 like that, bringing down the x plus 4, and now time to go ahead and multiply that out. So we got this x to the third plus 9x plus 4x squared plus, let's see, 36. And so therefore, putting this into standard form, we would end up with this guy right here. And now we're going to run it through the system, if you will. That means is that we're going to plug in 0 to get the y-intercept. So again, I like to show all process in instruction, most of it. And that's going to leave me with a 36. So the y-intercept is 0, 36. And we end up with this, which is going to be a leading coefficient, which is positive, and odd for n. So we know that that is going to be this guy and this guy. And so let's put all the information that we know on the graph and see where that takes us. Okay, so here is one of the peculiar things, again, about these guys right here. Okay, so this means that we only have one x-intercept, okay, and it's only a multiplicity of 1, so it's just going to go right through it. Pardon me. And so we don't really know what the graph is going to do, other than it's going to have this type of behavior, and it could go like this, okay, something like that. It could go something like this, all right? We don't really know. And so that said is that it's really, we're not going to be able to sketch out the graph itself without knowing some calculus, which we don't know right now. And so anytime that we have problems that contain these imaginary roots, we're not going to be required to sketch it out, okay? But let's go ahead and take a look at what the computer-generated graph looks like. Okay, so this is the one that we know that had some imaginary roots, and you can see that we were just kind of like taking a guess at what the shape might be. But notice that all the stuff that we can account for is being accounted for, and with the end behavior and whatnot with our graph. So though we can't get an super accurate sketch of this thing, we can go ahead and what we can control, put on the graph and do the best we can with it. So yeah, that's how you do that. And looks like that's the end of the video. I will see you in the next lesson.